Hello everyone! Welcome to my video lesson. I am Neil Jason Panisan, your teacher for today. In this video, we are going to explore one of the topics in Precalculus, which is the piecewise function. There are instances where the expression for the function depends on the given interval of the input values. When this happens, we call these types of function piecewise defined function. Piecewise functions are defined by different functions throughout the different intervals of the domain. We actually apply piecewise function in our lives more than we think so. Tax brackets, estimating our mobile phones, and even our salaries with overtime pay makes use of piecewise function. This is why we've allotted the special contents for this function. In these contents, you'll learn the following: objectives of the lesson, definition of the piecewise function, learning how to evaluate piecewise defined functions at given interval, including table values, graphing, and finding the domain and range, solve real-life problems, evaluation or assessment, and then we also have summary and generalization, and references I have used in the presentation. First, we have the objectives. At the end of the video lesson, you will learn the following: define the piecewise function, evaluate the piecewise defined function at given intervals, and solve real-life problems using piecewise function. What is a piecewise function? To fully understand what piecewise functions are and how we can construct our own piecewise defined functions, let's first dive into a deeper understanding of how it works. A piecewise function is a function that is defined by different formulas or functions for each given interval. It's also in the name piece. The function is defined by pieces of function for each part of the domain. We have here example of the piecewise function. So as you can see, there is a tree function. We have here f of x is equal to 2x for x is greater than 0, and f of x is equal to 1 for x is equal to 0, and f of x is equal to negative 2x if x is less than 0. As can be seen from the example, shown as a pieces of function because it is defined uniquely for the three intervals we have: x is greater than 0, x is equal to 0, and x is less than 0. A function can be in pieces. We can create functions that behave differently based on the input of the x value. In this illustration, we can have a function made up of three pieces. Let us try to recall the different functions learned from the previous. First, we have a constant function where the graph is parallel to the x-axis. Next, we have a curve which illustrates a quadratic function. And lastly, we have a linear function where the graph is diagonal straight line. What are common examples of functions that you may encounter when graphing piecewise function? Aside from the linear, quadratic, and cubic function, there are also common examples that you might encounter. Here, I'm gonna show to you: piecewise linear function, step function, Boxcar function, and so on and so forth. Let us try to open the piecewise linear function. This is a piecewise linear function composed of line segments, so a continuous piecewise linear function. Another example, we have a function and a piecewise linear function to it, red. A function blue and a piecewise linear function to it is red. we have here the red is a linear function and the blue is a quadratic function. So that is a piecewise function. We also have here a piecewise linear function in 2 dimension, top, and the convex polytopes on which it is linear bottom. So as you can see, that is composed of a piecewise linear function, a lot of linear function. Next, we have here step function. Step function, example of a step function, the graph, this particular step function is right continuous. A piecewise function composed of constant functions. And we also have a floor function. Floor function is a very special piecewise function. It has infinite number of pieces. So that is a step function. We have another classifications of the step function. We have the Boxcar function. We have here Boxcar function, a graphical representation of Boxcar function. And we also have Heaviside step function using the half maximum convention. And then we have sine function. So that is an example of a step function. Next, we have the absolute value function. Absolute value function is the most famous piecewise function. It has two pieces below 0 or negative x and from 0 onwards. So when you say absolute value, it talks about the distance, so it is always positive. The graph of the absolute value function for real numbers. And the absolute value of a number may be thought as its distance from 0. So as you can see, the distance. Next, we have triangular function. So exemplary triangular function. As you can see, we have triangle here. Remember the fractals of Mandelbrot. It is look like a fractals of Mandelbrot. Next, we have broken power law. So we have here an illustration for the broken power law. Some models of the initial mass function use a broken power law here in Krupa 2001 in red. So as you can see, we have the green part here that is a constant function. And then we have here the pink one, we have a curve which is a quadratic function. And then we also have a quadratic function here. And then the blue one, we have a linear function. We also have here spline, a piecewise function composed of polynomial function possessing a high degree of smoothness at the places where the polynomial pieces connect. So we have here an example of a spline. That is a single knots that establish a spline of 3 cubic polynomials meeting with c-squared continuity. Triple knots at both ends of the interval ensure that the curve interpolates the end point. So as you can see, we have connecting lines here, that is piecewise function. We also have here the B-spline. Spline curve drawn as a weighted sum of B-splines with control points or control polygon and mark components curve. So as you can see, we have here composed of spline. Another one, we have here the PDIFF. So we have here splines are piecewise smooth hence in PDIFF but not globally smooth on piecewise linear, hence not in PDIFF or PL. So we have here an example of PDIFF. Next, we have the bump function. Bump function, we have here an illustration of the bump function. So as you can see, we have a linear and then it bumps. So it makes it a quadratic function and then goes over with a linear function. These are infinitely differentiable but analytically holds only piecewise. Now that we've learned about this unique function, let's proceed to the given examples. How to evaluate the piecewise function? First, we have to solve the given intervals. Second, input the values on the table. Third, graph the ordered pairs on the Cartesian plane. And find the domain and range. How do we make sure that we return the right value for the function given x? Here are the tips to remember when solving for and evaluating piecewise function. First, we have double check where x lies in the given interval. And second, we have to evaluate the value using the corresponding function. Example number 1. Evaluate the given piecewise function at the given values of x as shown below. We have f of x is equal to 2x for x is not equal to 0. We also have f of x is equal to 1 if x is equal to 0. We're asked to find a f of -2, -1, 0, 1, and 2. So let us try to check whether it belongs to the given function 2x or 1. F of -2 is not equal to 0, therefore we're going to use f of x is equal to 2x. Substituting the values, we have f of x is equal to 2x, f of -2 is equal to 2 times -2, therefore the answer is -4. B. F of -1. -1 is not equal to 0, therefore we're going to use f of x is equal to 2x. Substituting the given values, we have f of x is equal to 2x, f of -1 is equal to 2 times -1, therefore the answer is -2. F of 0 belongs to x is equal to 0, therefore we're going to use the constant function. F of x is equal to 1. F of x is equal to 1, therefore f of 0 is equal to 1. Letter D. F of 1. 1 is not equal to 0, therefore we're going to use f of x is equal to 2x. Substituting the given values, you have the answer f of x is equal to 2. Next, we have f of 2. 2 is not equal to 0, therefore we're going to use f of x is equal to 2x. Substituting the given values, we have the answer 4. So we're going to plot this one in our given table values. If x is -2, therefore our y is -4. If x is -1, therefore our y is -2. If x is 0, therefore our y is 1. If x is 1, therefore our y is 2. And if x is 2, therefore our y is 4. That is our table values. Now, let's proceed to graph. How to graph the piecewise function? As we have mentioned before, piecewise function contain different functions for each of the given intervals. This means that when graphing piecewise function, expect to graph different functions for each interval as well. Here are some quick reminders when graphing piecewise function. First, we have it helps to identify how each function would look like. Second, for inclusive intervals, we have greater than or equal to and less than or equal to, including the endpoints by using solid dots. So we have here solid dots. For exclusive intervals, we have greater than or less than, exclude the endpoints by using unfilled dots. We have here unfilled dots for this one, greater than and less than. So based on the given function, f of x is equal to 2x for x is not equal to 0, and f of x is equal to 1 if x is equal to 0, the table values here is -2 and -4. Let's graph here, -2 and -4. we have -1 and -2. So we have here -1 and -2. We have 0 and 1. We have 0 and 1. We have 1 and 2. So here we go. We have 2 and 4. We have here 2 and 4. So here is the solid dot. Okay. So next we have to connect the lines, the dots. We have here connecting the dots. So we have here the line. Of course, this is the line is for the first function f of x is equal to 2x, where x is not equal to 0. That's why we put hollow here. And that's it. This is our graph. So to find the domain and range of this given function, we have here, since the graph covers all the values of x, the domain would be all real numbers, or -infinity to +infinity. The same reasoning applies to the range of function. Since it extends in both directions, the range of the function is -infinity to +infinity in the interval notation. Example number 2. Evaluate the given piecewise function at the given values of x as shown below. We have f of x is equal to 2x for x greater than 0. F of x is equal to 1 for x is equal to 0. And f of x is equal to -2x for x is less than 0. You can assign different values over here, but I'm going to use -2, -1, 0, 1, 2 for smaller value. -2 belongs to negative f of x. F of x is equal to -2x because -2 is less than 0. So therefore, we're going to use -2x. Substituting the values here, you have an answer 4. Letter B, f of -1. -1 is less than 0, therefore we're going to use f of x is equal to -2x. -2x is equal to -2 times -1, therefore the answer is 2. Next, letter C, f of 0 belongs to x is equal to 0, therefore we're going to use the constant function f of x is equal to 1. F of 0 is equal to 1. Letter D, f of 1 belongs to x is greater than 0. Therefore, we're going to use f of x is equal to 2x. Substituting the value of x, we have 2 times x is equal to 2 times 1, that is equal to 2. Letter E, f of 2. 2 is greater than 0, therefore we're going to use f of x is equal to 2x. F of x is equal to 2x, therefore 2 times 2, that is equal to 4. We have here the table values for x and y. If our x is -2, then therefore our y is 4. We have here -2 and 4. If our x is -1, therefore our y is 2. If our x is 0, therefore our y is 1. And if our x is 1, therefore our y is 2. If our x is 2, therefore our y is 4. So as you can see, there are 3 different colors here. For the first color, we have the red, 2 given values, that is for the function -2x. And for the green color here, that is for the constant function f of x is equal to 1. And then for our blue colored here, we have f of x is equal to 2x because x is greater than 0. So in order for us to graph this given piecewise function, we have here -2 to 4. We have -2 to 4. -2 to 4. And then we have here -1 to 2. -1 to 2 here. And then we also have 0 and 1. We have 0 and 1. We have here. Next, we have 1 to 2. We have here. And then 2 to 4. We have 2 to 4. Next, we have to connect the dots. We have here for the function negative 2x, we have here. And then for the function 2x, we have here. And then the constant function, we have 0 and 1. Of course, we're not going to include 0 of these two given functions, 2x and negative 2x, because it is greater than and this is less than. For the domain and range, this graph returns the final graph for the given piecewise function. From the graph, we can see that f of x has a domain of negative infinity to positive infinity and a range of 0 to positive infinity respectively. Example number 3. Evaluate the given piecewise function at the given values of x as shown below. So f of x is equal to, our first function is a quadratic, second function is a constant function, and the third function is a linear function. F of x is equal to x squared for x is less than or equal to 0. F of x is equal to 5 for x is greater than 0 but less than 2. And f of x equal to x over 2 for x is greater than or equal to 2. We have here we're asked to find, to solve the given values here. F of negative 2, so we're going to try to look for the interval asa siya nabilong. We have negative 2. So we are going to use f of x is equal to x squared. F of x is equal to x squared, substituting the given values of negative 2, therefore the answer is 4. F of 0 belongs to this interval. We have f of x is equal to x squared, therefore substituting the values 0 squared is equal to 0. F of 1 belongs to the constant function x is greater than 0 but less than 2, therefore f of x is equal to 5 and f of 1 is equal to 5. Letter D, f of 2. 2 belongs to x is greater than or equal to 2, therefore we are going to use f of x is equal to x over 2. We have 2 divided by 2, therefore f of x is equal to 1. We have letter E, f of 4. We're going to use the interval x greater than or equal to 2. F of x is equal to x over 2. We have f of x is equal to x over 2. 4 divided by 2, that is equal to 2. We have to input this one into the given values or the table values. If x is negative 2, therefore our y is 4. If x is 0, therefore our y is 0. If x is negative 1, if x is 1, therefore our y is 5. And if x is 2, therefore our y is 1. And if x is 4, therefore our y is 2. There are also 3 different ordered pairs here in our table values because we have 3 different piecewise functions. So the first, the red one, we have here x squared, and then the green one we have the constant function 5, and then the blue one belongs to the function x over 2. Now let's graph the given table values. We have here negative 2, 4. We have negative 2 and 4. We also have 0 and 0. And then we have 1 and 5. 2 and 1. We have 4 and 2. Okay. Now let's graph. Let's connect the dots. We have here 0, and 0 and negative 2, 4, we have here curve because it belongs to the function x squared. And then for the constant function, we have here. And then 2, 1, 4, and 2, so we have function. So we have to exclude 0 here and 2 since for our restriction, x is greater than 0 but less than 2. It does not belong here in the graph of f of x. That's why it is a hollow dot. Alright. So next we have to find the domain and range of the given piecewise function. Since all of the values x extend in both directions, the domain would be all real numbers or negative infinity to positive infinity. And since the graph only covers the values of y above the x-axis, the range of the function is 0 to positive infinity in the interval notation. Let's provide more examples for domain and range. If f of x is equal to x plus 1 for x is greater than or equal to negative 3 but less than 0, and if f of x is equal to x squared, if x is greater than or equal to 0 but less than or equal to 2, we have to plot this one. So from negative 3, that is the lowest possible value of x, we have negative 3. If our x is negative 3 and we substituted to the given function negative 3 plus 1, so you have negative 2. And we also have 0. If our x is 0, then we have 0 plus 1, then the answer is 0 and 1. So we're going to plot it here. We use the open dot because it is less than. So we have to connect the graph. And the next function, we have x squared. So the lowest possible value for x is 0. So therefore, if 0 squared, that is equal to 0. So we have here. And we have 2. 2 squared, if our x is 2, 2 squared is equal to 4. So we have here. So we have to connect. Since it is x squared, therefore our graph is curved or quadratic. That's why it is curved. So in order for us to get the domain, we have to get the lowest possible value of our x. We have here, we have negative 3 and negative 2. So you have 0, 1, and 0, 0, 2, and 4. So since it is solid dot, we are going to use the bracket. And then negative 3 for our lowest value for x. And then next is we have 2. Our highest value for x is 2. And we use the bracket as well. So then that is our domain. Next we have our range. Our range is our y values. The lowest y values of our graph is negative 2. That's why it is negative 2 here. And then on the upper portion, we have the highest possible value of y is 4. We have here 4. And we use the bracket sign. So it is easy for us to identify the domain and range when we are going to graph the given piecewise function. Another, we have f of x is equal to x for x is greater than or equal to negative 3 but less than or equal to 0, and f of x is equal to 2 for x is greater than 0 but less than 1, and f of x is equal to square root of x for x is greater than or equal to 1 but less than 4. Alright, so we have here, if our value for x is negative 3, then our y is negative 3 in this given function. So we have here a plot, negative 3 and negative 3. How about 0? So if our x is 0, then our y will become 0. We have here 0 and 0. And if so, we are going to connect the given function, the line. How about if x is greater than if x is equal to 0, then we have 0, 2 for our y. So here is, we use the hollow because it is greater than, x is greater than 0. And then how about if our x is equal to 1, then our y will be equal to 2 because that is constant function. And we're also going to use the hollow. And then we are going to connect the dots. Next, on the third given piecewise function, or which is the linear function, if our x is equal to 1, then our y will be equal to 1. Square root of x, that is equal to square root of 1, and the square root of 1 is just equal to 1. And we also have here 4, the square root of 4 will be equal to 2. And we use the hollow side, hollow dot, because of the sign less than. And then we are going to connect the two linear functions. So what is our domain here? So our domain is the lowest possible x value is -3, and the highest, so we have here -3. We use the bracket since -3 is included, that is solid dot. And then the highest possible value for our x is equal to 4. And we use close parenthesis since we use parenthesis since our dot here is open, which means it is excluded. And our range here is -3 since our lowest possible value of y is -3. And we use the bracket. And then next, the highest possible value for y here is 2, and we use the parenthesis. So that is for domain and range. Now let's proceed to problem solving. So first problem. Spoken word poetry is being held at the nearby cafe. They charge 300 pesos per person for a table of 1 to 5 guests. They also offer a fixed fee of 2,500 pesos for a table with 6 or more people. Write a function that relates the number of people of x and the cost of attending the event, f of x. So solution. Let's go ahead and break down the problem and find the expression of f of x for each interval. For a table of 1 to 5 guests, we can express that if x is greater than or equal to 1, x is greater than or equal to 1 but less than or equal to 5 in terms of x. Since it would cost each guest 300 pesos, the total x guest is 300x. Now, for a table with 6 or more people, we can express the interval as x is greater than or equal to 6. For this interval, f of x will always be equal to 2,500. We can summarize this into a piecewise function. F of x is equal to 300x for x is greater than or equal to 1 but less than or equal to 5, and f of x is equal to 2,500 for x is greater than or equal to 6. The piecewise function represents the cost of f of x for x number of guests. Number 2. A doctor's fee is based on the length of time up to 6 minutes cost 2,000 pesos. Over 6 and up to 15 minutes cost 3,200 pesos. Over 15 minutes cost 3,200 pesos plus 200 pesos per minute above 15 minutes. Which we can write like this. F of x is equal to 2,000 if t is less than or equal to 6, and f of x is equal to 3,200 if t is greater than 6 but less than or equal to 15, and f of x is equal to 3,200 plus 200 times the quantity of t minus 15 if t is greater than 15. If the doctor visited for 12 minutes, what is the fee? So the answer is 3,200 because 12 minutes belongs to this given interval. And if the doctor visited for 20 minutes, what is the fee? So we have to use the last given piecewise function, 3,200 plus 200 times t minus 15, and that is equal to 4,200. Next, we have evaluation. We have here 3 exercises on solving, graphing, finding the domain and range, and a problem solving. Number 1, evaluate the given piecewise function at the given values of x as shown below. So as you can see here, we have here the exercises. Number 2, graph the piecewise function shown below using the graph, determine its domain and range. Third, suppose that you have a summer job that pays $12 per hour. You are required to work for at least 30 hours per week. The company pays time 1.5 times your hourly rate for overtime. A. Set up a piecewise function that represents your weekly pay. B. Graph the piecewise function you have set up. C. How much would you earn if you work for 48 hours that week? Please take a screenshot on these exercises and feel free to send your answers on my email address so that I can give you a feedback on your answers. Next, summary and generalization. Let's check whether our objectives are attained. Define the piecewise function, yes. Evaluate the piecewise defined function at given intervals, yes. And solve real-life problems using piecewise function, yes. Piecewise function is a pieces of function, may it be constant, linear, or quadratic function with restrictions. It can be defined by different functions throughout the different intervals of the domain. Remember, when solving for and evaluating piecewise function, double-check where x lies in the given interval. That's all for today. Thank you very much for taking time to watch my video. If you have any question, please message me on my email address. Thank you so much.